more precise. If I want a better estimate of the true area, well then I should just use more rectangles. The more rectangles I use, the more accurate this will be. And now comes the sort of brilliant moment, if we were live in class, and I'm sorry we're not, in which you realize, really we talked about this on the first day of the semester, so it's not a surprise, that like if I want truth, man, if I want to know the exact area under the curve, then I want to use an infinite number of rectangles. And that sounds like something a kid would say, I want an infinite number of rectangles. You can have that, an infinite number of rectangles. They will of course be infinitely thin. And so this process involves us adding up an infinite number of infinitely small things. That sounds very scary, and it is. But we have developed over the course of this entire semester strategies for dealing with infinitely small things. And the answer is to use limits. So what I'm now going to do is I'm going to erase all this, and we're going to redo this problem, and we're going to get the real answer. And the real answer is going to come from using an infinite number of rectangles. And since that is kind of nonsensical, what we're really going to do is we're going to use n rectangles, and then we're going to let n go to infinity by taking the limit. Okay, so without further ado, I will now find the, so I'll redraw the picture, this time maybe even bigger, because I need to do something even more sort of careful. Well, same picture, same size, I guess is fine. So that's 1, 1. Okay, colors are really hard to see on the video, but I like to use green, which even in class is barely visible for the true area under the curve. And now I'm going to approximate it. How many rectangles am I going to use? Answer n. Well, if I'm going to use n rectangles, then how wide should each one of them be? Well, since this entire interval has length 1, then the width of each rectangle, which you might call delta x, should be 1 over n. That's just a way of saying, if you really want to have n rectangles, then let's make the first one be describing the function on the interval from 0 to 1 over n. The second one should be describing it on the interval from 2 over n. Then hold on, gotta think deeply about my limited space here. Okay, so 1 over n, 2 over n, 3 over n. And I'm going to skip ahead to like generic rectangle I over n. And then I'm going to skip ahead again to the last rectangle, the nth rectangle, which will be n over n. And it shouldn't matter whether I use LRAM or RRAM, so I am going to use RRAM because it's essentially just superior, because I don't get this kind of off by 1 error. You will see. Alright, so I'm going to draw on these rectangles. I got my first rectangle. Second one. Oh yeah. Never done this lesson this way before. Like I was saying, I think it's working out. Who knows? Okay, so not sure how clear that is in the video. Maybe I need to color them in even more than usual. But we have these rectangles, and I've drawn, yeah, that's pretty clear. I've drawn the first 3, and then I kind of skipped ahead to the ith, and then I sort of skipped again to the nth. Okay, and let's just figure out some things now. Like, what is this? Well, maybe I don't even need to, because this function's so easy. So let's just start. What is the area? Well, the area is going to be the sums of the areas of all these rectangles. It's just the base times height. So the base is the width of this rectangle, and the width is 1 over n. So we take 1 over n times the height, and what's the height? Well, I'm using RM, so for the first rectangle, I plug 1 over n into x squared, and I get 1 over n squared. So I'll write it like this. And then, how about the second rectangle? Its width is also 1 over n, and its height is whatever I get when I plug 2 over n into x squared. So that's 2 over n squared. And so actually this is exactly like what we did before. The third rectangle will be the width of the rectangle, which is 1 over n times 3 over n squared. And in fact, this is exactly what happened before, except in this case, before we had 6, now we have n. Okay, and now we get to the sort of generic one, the ith rectangle. Well, the ith rectangle will still have width 1 over n, because all these rectangles have the same width, but the height of the ith rectangle will be I over n squared. And then skipping ahead to the last one will give me n over n is the last rectangle, which is of course just 1. So the width is 1 over n, and the height is n over n squared. Okay, so I'm doing this kind of in the baby version way first, just so everyone can be totally clear about the geometry and the connection between this picture and the algebra. But of course, this can now be simplified because all of these rectangles have the same width, which is 1 over n. So I can factor that width out, and now I'm just dealing with the heights. And so what do I have in here? I have 1 over n quantity squared plus 2 over n squared plus, and now I'll just go to I over n squared plus, and then the last one will be n over n squared. And, well, why is this useful? Why do I keep talking about I? Because I kind of like, right, these summations get annoying after a while, and if you are sophisticated and experienced enough, then you don't want to use them. Instead, you just want to use summations. And that's exactly what we're going to do. We're going to say that this is the sum from I equals 1 to n. And, okay, all the hard work was done for us already, right? What does so there's a 1 over n all the way on the outside. And then, what does the form look like? Well, in each case, it's just I over n quantity squared. So when I is 1, you get the first term. When I is 2, you get the second term. When I is n, you get the last term. So now I just need to compute this. And even this can be computed as, this is 1 over n times the sum from I equals 1 to n of, this is really just like 1 over n squared times I squared. I guess there are different sort of choices I could have made here, but this seems okay. And so this entire thing just boils down to the note that the I is the index of the summation sign, so it's the I that's changing. So this whole thing becomes 1 over n cubed times the sum from I equals 1 to n of I squared. In other words, and I guess there were other ways I could have done that. I could have split up the 1 over n squared without using the summation and pulled it all out, but this either way you get the same thing. Okay, and what does this represent? No, maybe I should just push on, because we have a formula for the sum of the squares, and the answer is that this formula is, so I have this 1 over n cubed. If I add 1 squared plus 2 squared plus 3 squared plus 4 squared all the way to n squared, I know exactly what I'm going to get. What I'm going to get is n plus 1, 2n plus 1 over 6. Okay, and now I have this amazing thing here in red. What is this amazing thing here in red? Maybe I should, do a couple more small algebra steps. Let me do a couple more small algebra steps. For example, I can cancel an n on the top and the bottom, and this I'll multiply out as well. So that gives me on the top, I get 2n squared plus n plus 2n, so that's plus 3n plus 1 over 6n squared. Okay, so now, and I'm going to put a purple box around this, now I want to pause and think about what I have actually done. What have I done? I have constructed, given this function fx equals x squared on the interval 0, 1, using n subintervals and following the RRAM algorithm, I have come up with an expression. And what does this expression represent? It represents the area under the curve using n rectangles. In other words, if I plug 5 in for n now, then that would give me the area under the curve as approximated by 5 rectangles. If I plug 6 in for n, in fact I'm just going to get that exact number, 91 over 216. You can even just do it. 36 is 72 and 18 is 90 and 1 is 91 over 216. And so what you should think of this formula in the purple as doing is outputting. You input an n, it outputs the area under the curve as approximated by n rectangles for this function on this interval. And now we wanted to know the sort of true area under the curve. Well, the true area under the curve comes from just letting the number of rectangles approach infinity. And so if you take the limit as n approaches infinity of 2n squared plus 3n plus 1 over 6n squared, well, okay, this is the kind of thing we're experts on. We can see that this is a rational function, so only the leading coefficient matters. This is just 1/3. Whoa! That means that the true area under the parabola y equals x squared from 0 to 1 is exactly 1/3. Okay, good. I am now going to do one more problem, which is no different from this conceptually, but it is sort of harder because of all the algebra and stuff. Okay, good. I think this was a success. Whew. Yeah. All right. Okay, we push on. Sure. We push on. Okay, so new problem. In principle, not any different from the previous problem. In fact, this might strike you as slightly repetitive. But we're going to get better at this. Take the curve y equals x squared plus 1, but now on the interval 1, 4. And the goal is to find the area under this thing. Okay, so let's go. What does y equals x squared plus 1 on the interval 1, 4 look like? Well, first of all, here's 1. If I plug 1 into, maybe I'll just call this f. So if I plug 1 in, then I get back, of course, 2. So 1, 2. But looking ahead, because I've done this before, let's see, we're going to go all the way out here to 4. So when I plug in 4, I get 17. So that is reasonably accurate, or at least good enough for me. So what makes this problem a little bit more difficult now is that we are finding the area on a sort of more, well, not starting at 0. So things are a little bit kind of more complicated. But in principle, it's exactly the same. Okay, that's what I want to do. I want to find the area of that green shape. The area under y equals x squared plus 1 on the interval 1, 4. How are we going to do this? Well, we're going to do it just like before. We are going to use n rectangles. And if we are going to use n rectangles, then that's just another way of saying I'm going to use n subintervals. There's sort of going to be n different pieces. And if there are n different pieces and I want to split it up evenly, then I have to consider the total width of the interval. Well, if the total width of the interval is 3, in this case, then delta x, which I'm using to refer to the width of every one of these little rectangles, should be 3 over n. And well, all I mean by that is that you should be skipping by 3 over n every time, so that after you've done that n times, you've gone all the way from 1 to 4, of course. Okay, well, let's start drawing some rectangles. Here is the, oh, and I'm going to use Rm. Okay, let's draw the first rectangle. Well, the first rectangle will look like this. And what is this x-coordinate? Well, if I decided to skip by 3 over n every time, then this is going to have the somewhat awkward value of 1 plus 3 over n. And it's that number which is going to get plugged into the function. So what is that? Well, I'll gotta worry about space here a little bit. So, okay, then I'll go to the next one. What's the next rectangle look like? It looks like that. And what's its x-coordinate? Or rather, what's the x-coordinate of the right endpoint of that interval? Well, now it's 1 plus. Now I've moved over by 3 over n twice. So I'm going to call that 2 times 3 over n for clarity. And now, skipping ahead, I'm going to get to the ith rectangle. And what does the ith rectangle look like? Well, the ith rectangle is what you get when you start at 1 and you skip by 3 over n I times. So that's why I'm going to write that as 1 times 3 over n, 2 times 3 over n. Over here I get I times 3 over n. And finally, skipping ahead some more, hopefully this is clear, I get the area of the last rectangle, the nth rectangle. And what should it be? It should be 1 plus, how many times now have I moved over? Well, n times I've moved over. And so that's n times 3 over n, but of course that's just 3, and so that's telling me that this is just 4, so it's all good. Okay. Well, this is good. It means that, oh, and if I'm using Rm, then it means that I can label each one of these points. So this point right here has coordinates 1 plus 1 times 3 over n, comma, f of that number. And this point has coordinates 1 plus 2 times 3 over n, comma, f of that number. But because I'm going to do this in general and be sort of sophisticated and use summation notation and stuff, then I only really care about the value at the generic rectangle, and that's going to be 1 plus I times 3 over n, comma, f of that number. In other words, I claim that the area under this curve using n rectangles and using Rm is going to be, maybe it is worth it to write it out kind of baby style first. What's the width of this first rectangle will be 3 over n, and the height of that first rectangle will be f of 1 plus 1 times 3 over n. And the height of the second rectangle, or the area of the second rectangle, will be the width, which is 3 over n, times the height, which is f of 1 plus 2 times 3 over n. And skipping ahead to the generic rectangle, the ith one, it's going to still have width 3 over n, but it's going to have height f of, well, the height of the rectangle is the value of the function at the right-hand endpoint of the ith subinterval, and by the time I get to the ith subinterval, I've scooted over by 3 over n I times. So that's why it's 1 plus I times 3 over n. And then all the way to the last one, which is, well, it's 3 over n times, I'm running out of space, so I'll just call it f of 4. Okay, so this gets annoying to write out every time. So we need to just elevate to the most sophisticated way of doing this, which is to which is to use sigma notation. So what are we going to be doing? We're going to be adding up n things. And the n things we're adding up are areas of rectangles. And what is the area of the nth rectangle? The ith rectangle. Well, the area of the ith rectangle is just 3 over n, the width, times the height, which is f of 1 plus I times 3 over n. And we start counting at I equals 1, as you can see, and we stop counting at n. Alright, so if you get this was, I think, the hard part, is the thinking part, the understanding, the structure, the recognizing that this interval has length 3, and so I need to scoot over by 3 over n every time. The connection to the picture and to the problem. And once you get this far, now we can just sort of do it. Well, what is it that we're really doing? We're trying to take the sum from I equals 1 to n of, well, I have this 3 over n, and then I have f of 1 plus I times 3 over n. But of course, f was just my shorthand for this function x squared plus 1. So now what I have to do is plug 1 plus 3i over n into x squared plus 1. Okay, so let's see, I'll use brackets. So I get, and in fact, I'll write it as 3 over ni plus 1, and then that's squared plus 1. Okay, this is quite sophisticated, but I chose to rewrite it slightly because my true variable here is I, right? I is the index of my summation. I is the thing that's gonna change. Okay, so now it's just a matter of simplifying all this. Let's see, what can I do? One thing I can do is I can pull this 3 over n out, because n is a constant at the moment. It's just the number of rectangles that I use. So we get 3 over n times the sum, and what's in this big summation? Well, I suppose the thing to do is to just expand this all out. If I expand this all out, I get 9 over n squared, I squared, plus 6 over n I, plus 1, plus another 1. In other words, I have a quadratic in I. Okay, I proceed by combining like terms, and I get 3 over n times the sum from I equals 1 to n of 9 over n squared, I squared, plus 6 over n I plus 2. Now what? Well, now I should try to pull some things out. And so what I'm now going to do is split this up into 3 different summations. And I guess I'll just go over here. Let's see. So first of all, well, I'll just do it and you'll just see. So this is going to be the sum from I equals 1 to n of, really that's like 27 over n cubed times I squared, plus, really that's like 18 over n squared times the sum of the i's, and that's really like 6 over n times the sum from I equals 1 to n of just 1. In other words, sort of, I'm doing it in 2 steps, I guess. Maybe that's somehow that's more confusing. Maybe if I insert one more line here, what I'm really kind of doing is I have the 3 over n, but then outside of all of that, I want to split up these summations into the sum 9 over n squared I squared plus the sum 6 over n I plus the sum of a bunch of 2's. And okay, here I'm just using the property that addition is very flexible. So I can add up 3 things n times, or I can add up the first thing n times the next thing into, okay, so I think that's pretty clear that the order in which you do it doesn't matter. And then I'm pulling out all the things that aren't i's. Okay, this is quite abstract, and what we get is this expression. Okay, but we're not done yet. Now I reach for the formulas. And the formulas say, okay, so this is 27 over n cubed times, what is the sum from I equals 1 to n of I squared? We know it as n plus 1, 2n plus 1 over 6. What is the sum from I equals 1 to n of I? That might be a lot better. It's n plus 1 over 2. And this is going to be 6 over n times. What happens if you just add 1 up over and over again n times? You get n. Okay, so squeezing this into this tiny little space, I can now do things. Let's see, 27 over 6 can be better written as 9 halves. So I get, oh, this sucks. So I get 9 halves times that n and one of those cancels. So I get 2n squared plus 3n plus 1 over n squared, plus, here I get 9 times n over n plus 1, and here I get just 6. Okay, so pardon the fact that I ran out of room, but this expression, just like before, what I have now done is after all this work, I've constructed an expression which tells you for a particular n what the area under this curve will be, where n is the number of subintervals that you used. And the final step, which is the glorious part, is to take the limit as n goes to infinity. And if you take the limit as n goes to infinity, this rational function is going to 2. So I get 9 plus, this is going to 1 plus 6. And so the answer to this problem is 24. The area of this region between x equals 1 and x equals 4 under the function y equals x squared plus 1 is exactly 24. Okay, and so we have seemingly in one class solved the area problem. Okay, good job.